All right, let's go ahead and get started. Anybody have any questions before we do? Okay. So talking mean value theorem, got a couple of things left to cover here. So we're driving a car for 4 hours, we cover a distance of 280 miles. Is there anything we can say for certain about our speed over that time?
Can you get the average speed based on the miles per hour?
We can get the average speed. So what is the average speed here?
7 miles per hour.
Okay, so the average speed is 70 miles per hour. So yes, I mean, I have no idea. That's about all I can say right now. I mean, I know we drove 280 miles. We know it took 4 hours. So we can say the average speed is 70 miles per hour. Is there anything else at all we can say?
No.
So let me ask you this question. Was the instantaneous speed ever 70 miles an hour?
Had to be at least once, right?
Why does it have to be?
Because if it's the average speed, in order to be the average speed, it has to be achieved at least once.
So sounds like you're thinking mean value theorem, which is good. Can we say we meet those conditions though? So what are the conditions for the mean value theorem to apply? We can make a checklist out of this. Because I think for this answer to my question is to be yes, we have to meet all those conditions. So what are the conditions for the mean value theorem to hold?
The closed interval needs to be continuous and differentiable.
Okay, so F is closed, or F is continuous on some closed interval. Can we assign some closed interval based on this description here? What would that closed interval be?
0 to 3.
0 to 4. So yeah, that's I'm kind of glad that came up. So the closed interval that you're continuous on is some input, some set of values for the input, which usually makes sense. If time is one of your variables, it almost always makes more sense to have that be the independent variable. So F is continuous on 0, 4. I believe that's true. So in fact, actually, I'm jumping the gun here. If we're going to say that's true, we should probably be specific on what this function is. What is the function we're talking about here? What is F? I mean, we've kind of already given away what the input to F is. So the input is time, right? So if we're going to describe this function, what's the output of this function?
Distance.
So let's think about that. So time is an input to this function F. Don't really need to know what this function does. I mean, I didn't tell you anything about it. I kind of gave you the endpoints, right? So this function translates time to distance somehow.
So F is a function of time.
F is a function of time. Distance is the output to that function. So now that we have that function F, now we've talked about what it is. Does it make sense to say that function is continuous? If you're driving a car, is your distance continuous? Let's think about what would it mean for your distance not to be continuous?
Teleport.
Yeah, you basically have to be warping through space, right? You have to somehow get from A to B without going to any of the places between them. That would be impossible. Things like that, right? So yes, I believe that this function is continuous because of the laws of physics and you not being able to violate them. What other conditions do we have for the mean value theorem?
F has to be differentiable on the open interval of 0 to 4.
Okay, so then in our case, F would have to be differentiable on open interval 0, 4. So our function is distance our function is one where distance is a function of time, right? So we've talked about that being continuous. What would that mean for that function to be differentiable? If you're talking about a distance function, what kind of thing is its derivative? The speed, right? Does my speed have to be something continuous? Yes, how come?
Because you can't go from.
Right, you can't, so not without doing what? Not without hitting all the speeds in between them, right? So I believe, yes, that function's differentiable as well. I can't just, yeah, I cannot immediately make my speed change. So yes, I believe that this function that we're talking about, even though we have no idea really how it's behaving, I can call it continuous, I can call it differentiable. So based on those two things, I had a third checkbox. Is there more conditions? Just those two, right? So we've met both those conditions. So can we answer my question now? And I mean, a lot of you kind of said yes early on, but so the speed of the car was 70 miles an hour. How many times?
At least once.
At least once, right? And it seems kind of intuitive. I mean, if your average speed was 70 miles per hour, then it seems intuitive that, yeah, I definitely, my speedometer definitely read 70 miles an hour sometime. But hopefully that context made it more clear kind of why the mean value theorem says the things it says. Any questions there? All right, finally. I'm giving you 1 point on a function, so 0, -3, and I'm telling you something about the derivative. And I want to know how large f of 2 can possibly be. So let's draw a picture of what I'm talking about here. So f of 0 is -3. And I'm interested in f of 2, right? So what's the largest thing? What's the largest value that f of 2 could possibly take? How can we start thinking about this? That's what f of 2 can be?
We don't know what f of 5 is.
So we don't, f of 2 could be infinitely many things, but I think it's limited.
Yeah.
Somehow. So how can we figure out, let's just say this, there is no limit to what f of 2 could be on the lesser side.
Oh, yeah.
I can make f of 2 as small as I want, because all I'm telling you is that the derivative, I've been telling you f prime is 5 and no larger.
Oh, then it can't be more than 7, is it?
How'd you get 7?
Because from 0 to 2, if the rate of change can't be more than 5, or greater than or equal to 5, then like that's how the rate 5, like 2 points.
Okay.
And for a rate of change of 5, that would get you to 7.
So our change in x is 2. So basically what you're saying is this, is that since change of x is 2, that means change in y is, I'll say, less than or equal to 10. Are we okay with that? So let's try to put this, I mean, so based on that, you're saying f of 2 is less than or equal to 7.
Yeah.
And for now, I'll just call that a question. But are we okay with this logic so far? I know you are. So. Anybody else? Any questions about where this came from? Is that wrong? I don't know. I mean, so we have some kind of intuitive argument. Let's try to ground it in mean value theorem. Is this function continuous? By the way, what closed interval am I even talking about? I should probably talk about that. 0, 2 is so I'll say this, the interval I care about, which I'll call capital I, is 0 to 2. Is my function differentiable on that closed interval? How do you know?
Greater than equal to f prime greater than, less than or equal to 5.
Right, so I told you what the derivative, like something about derivative everywhere, which means you can kind of infer from that the derivative exists. So the derivative, so it's differentiable on the interval. The interval is closed. Is it continuous on the interval? There kind of is a way to know that. If a function is differential, what does that mean about its continuity? It's continuous, right? So if you have differentiability, you have continuity for free. So because of that, I can say this. We can take the conclusion of the mean value theorem for free.
So is it not a continuity doesn't guarantee differentiability?
Because continuity does not. So I'll give you an example here. Kind of the stereotypical example for continuous but not differentiable is the absolute value, or anything based on the absolute value. So that function right there I just drew is continuous everywhere, but at that hard corner, the derivative doesn't exist. So differentiability guarantees continuity, but not vice versa. So we've met the conditions for the mean value theorem. So I get to say that this thing that I just wrote out here, there's a C that exists where that's true, right? So let's go a little further. Do I know what A and B are? Yeah, A is 0 and B is 2. I'm going to say f of 2 because I don't know what it is. I know that f of A is -3. And I know that B minus A is 2. Correct? But what do I know about f prime of C? It's 5 or it's less than 5, right? So I'm going to go ahead and replace that with 5. I'm also going to replace the equal sign with the inequality. So 5 is less than or equal to, no, 5 is greater than or equal to f of 2 plus 3 over 2. So basically this inequality, if you solve this, you're going to get some kind of bounds for f of 2, right? So it might hurt your eyes for me to go from right to left, but that's kind of what I have to do. So from here, I get that f of 2 plus 3 is less than or equal to 10, and f of 2 is less than or equal to 7. So I like the way that Solomon got there. Basically, Solomon took the extreme. Let's say the derivative is exactly 5, and how, like, what's the highest up points I can reach over here? Which, yeah, got you in the right place. So f of 2 could be 7, could be anything, or could be anything less than it. How are we doing with that? So that's all for mean value theorem. Any questions before we move on to 4.3?
Would that same thing that Solomon did be true for any kind of this type of problem, where you could take the extremes and just sort of take the difference between them and add that on to the? Yeah,
I mean, that's the mean value theorem illustrates basically why Solomon's reasoning is solid. Yeah. So I mean, I kind of left it hanging whether Solomon was right. The mean value theorem really convincingly says that yes, that maximum is 7. Anything else here? So moving on to 4.3, which we probably won't finish, but we'll get into it. So we talked a lot about derivatives. Every once in a while, we'll talk about what that means for graphs, but now we're going to really focus on that. So what do derivatives mean about the way a graph is shaped, the way a graph looks? So what does the derivative tell us about a function? Instantaneous rate of change, right? Graphically speaking. So let's pick a point on here.
One.
Where?
One, X equals one.
X equals 1, cool. So right here, what, if anything, can we say about, f prime of 1?
Negative,
Why is it negative?
because the graph is pointing down.
What do you mean by the graph is pointing down?
It's from left to right, the graph. is pointing down.
Okay, so from left to right, your y values are going down, right? We okay with that? Where on here is the graph is f prime positive?
From 2 to 3, and from 0 to 5.
So let me just fix it on 1. We're saying that f prime of 2.5 is positive. Does that make sense? So, and we've talked a lot, about this specific thing before. If your function is decreasing, like it is f prime of 1, that means the derivative is negative. Those two things they say the same thing. They're equivalent to each other. By the same logic, f prime of 2.5 is positive because your function is increasing. Is there anywhere on here where the function is, or where the derivative is equal to 0? Where would that be?
0.5 and 3.
Why is the derivative 0 when x equals 0.5?
Because it doesn't look like at that point the y value is going up about 4.
Right. So, and kind of in the language of things we've just gone over, what kind of point is f of 0.5? It's a critical point. Can you be more specific? To local max. So at local maxima and local minima, you have to have what has to be true about the derivative. So it equals 0 or what? Or it doesn't exist. But looking at this graph, it looks like it's differentiable everywhere. So anywhere you see those local min. So you said another point where this happens? Is that all of them? I'm gonna. No, I would say 2 is probably not a local min, but I'm going to say f prime of 1.8. Clearly, there's a minimum somewhere in that like half point interval. Any other local extremes? Doesn't look like there are any others, but yeah, good recap. I hope of what a derivative tells you about a function specifically when we're concerning ourselves with graphs. Any questions on any of the labels we threw on here? Okay. So, and one thing we can pick from the first derivative is increase and decrease. So if you have some interval and the derivative is greater than 0 for that interval, then we can say that's an interval of increase. For every x on the interval, that function is increasing. Similarly, if the derivative is negative on some interval, we know our function is decreasing. And those two things are equivalent. To say that the derivative of a function is to say that the derivative of a function is positive is to say that the function is increasing, and vice versa. And also, if you have f prime of x equals 0, what does that say about the function?
It's not doing either.
It's neither increasing nor decreasing, right? So, is it a local extreme?
It's fair.
Did I hear yes?
Yeah.
Always? No. So we've seen some examples of when the derivative is 0, but you don't have a local min or local max. But usually you will find that to be the case, but it's not always true. So let's do one here. So for this degree 4 polynomial, I want to find all the intervals where it's increasing and decreasing. So if I want to find where it's increasing and decreasing, what do I need to get my hands on? Need to get our hands on the derivative. So what is the derivative of f?
12x cubed, minus what, 48x squared, minus 252 x, minus 1.
That's just nothing.
Nope.
Oh, that's nothing.
Yeah, derivative of 5 is 0. So this right here is our derivative. What do we do with it?
Find the zeros and then plug in the values.
Right. So, and I think that's a really good way to go. If you want to find out where it's positive or negative, look for the boundary cases. And in this case, that's going to be where this is equal to 0. There's a nasty cubic though. How do we solve this?
Factor out of x.
Can we do better than that?
You take out
Factor out of 12.
I think 252 is divisible by 12. I'm pretty sure that I cooked this up so that happened. Yep, okay. So if I factor out 12x, I get 12x times x squared minus 4x minus 21. All right. Can I factor further? So where are my zeros?
0, -3, 7.
So I can't give you the intervals yet. I mean, I can kind of tell you what the intervals are, but I don't know what they do yet, right? So I know where the derivative is equal to 0. So based on where those critical points are, what intervals am I looking at?
-3 to -3, -3 to 0, 0, 7, 0, 7.
Okay, so negative infinity to -3 is the least of these. And then from -3 to 0. And from 0 to 7.
Yeah.
So those are the 3 intervals, right? I don't think that covers everything.
Oh, no, 7.
7 to infinity. Okay, good. So, yeah, basically, oh, what is that? No idea. Seems like a cool feature if I want it to happen. So basically what we did with these critical points is those allow us to divide the real numbers up into all the intervals we actually care about, right? So now, by the way, does it make sense? I automatically made all these intervals open. Why does it make sense to just make all those intervals open? Like, why am I not including -3, Garrett?
Because you don't know if it's into,
I don't know what.
if it's continuous.
I do know it's continuous.
Because that endpoints, the derivative is 0.
I know the derivative of 0 of those endpoints. So basically at all those endpoints, I know the derivative, the function is neither increasing nor decreasing. So I can already rule those out. All right, so now to get more information, I'm basically going to look at this function, the derivative of this function around these points. So where are my boundaries? -3, 0, and 7, right? And all these derivatives are 0, 0, 0. Solomon?
Don't you only have to look at the -infinity to 3 and then 7 to infinity? And then it'll tell you about the rest.
What do we think? If we get the far left and far right, will that tell us everything else?
Because you know how the y values are doing in the middle. And you know that like say from 0 to 7, that's increasing, and then -3 to 0 is decreasing.
Okay, so let's pick an interval, and then I'll have some follow-up questions. So let's pick the value 1. And that'll tell us everything between 0 and 7, right?
Yeah.
So what do I do with that x value of 1?
Like if it's the original one.
Not the original function. I am looking for increase and decrease, right? So I need to know about rates of change. So f prime of 1 is equal to 12 minus 48 minus 252. And here's a shortcut I hope you will grant me. Do I really care what this number is exactly?
I just care if it's positive.
Okay, this is clearly negative. So rather than me trying to figure out what that number is, I just need to know it's negative, right? So clearly, this thing is decreasing on the interval 0, 7, right? Does that mean that for x values greater than 7, I'm increasing? It doesn't always mean that, right? For this function, I believe it will.
Yeah.
But don't forget about things that look like this. So I could have a function that has, look, this function has lots of critical points, but I think it's increasing everywhere except where those critical points are.
Mhm.
So I think we have this idea that functions behave like they change when they change direction, they actually change direction.
Mhm.
And I believe this is one of those times, but I think it's a good idea to really check all your intervals to make sure it actually does the things you think it's going to do. So go ahead.
So then by the same caliber, we can't assume that, between -3 and 0 is going up as well.
Yeah.
Okay.
So all we can say right now for sure is that it decreases on 0 to 7, right? All right, so we need to check some other values. What's another value we should check?
-1.
-1. So that'll tell us something about this interval. It sounds like we suspect that'll be positive. So f prime of -1 will be -12 minus 48 plus 252, right?
Would it also be plus 48?
Plus what?
Would it also be plus 48?
Yeah. I think-
So negative times negative, positive times another negative makes it negative.
Either way, it doesn't affect the answer, does it?
Well, it will, but we should probably should have this right.
Yeah.
So -1 to the third power is -1, right? Times negative, another negative is positive. So yeah, we're kind of taking some liberties with the negative. We're just trying to get negative versus positive, but let's make sure that 48 is positive. So yeah, that's positive, right? So we know what about this interval?
It's crazy.
This is an interval of increase. All right, are we done? What else should we look at?
5.
-5 sounds good. And for good measure, we need one more test point.
30.
30 sounds good. So f prime of -5. Let's think about limits here. This interval here covers any negative number, no matter how large its magnitude is, right?
Yeah.
If I plug it into the derivative, isn't the third power of that number going to just overwhelm the other ones?
Mhm.
The second power and the first power?
Yeah.
So really it all comes down to whether this thing is negative or positive.
Mhm.
Will that be negative or positive? So that might have been a little hand wavy, so I'll pause. Do I need to go through what I went through again? If I can restate a little more quickly, basically, I could pick anything less than -3. Could have been -5, could have been -10 million. Let's say it was -10 million. These two things are not really gonna. These are the larger those magnitudes of those numbers get, these are just going to be totally dwarfed by whatever that is, whatever 12x cubed is. And let's make sure we say this out loud. How do I know that 12x cubed will be negative?
Overpowering exponent.
What's that?
Overpowering exponent.
What if it was 12x to the fourth?
Well, no, because then it'd be go back to even. It's.
Okay, good. So
It'll stay negative because it's an odd power.
that's what I really wanted to point out. So when you have a negative number, you raise it to an odd power, it remains negative. So that will be an interval of decrease. And finally, f of 30. F prime of 30 anyway. And kind of by the same token, I can make my numbers as large as I want, which means the only thing that's going to matter is the first term. That's going to be positive. So this one kind of behaves, you know, as you'd expect. We found the zeros, and you get this alternation, decrease, increase, decrease, increase.
I just want to make sure 0 is the 0 because of the 12x, right?
Yes. So yeah. So when we're solving this equation, these are our three factors. So since the product of all these things equals 0, it's enough for any one of these things to equal 0. That equals 0 when x is -3. X is +7.
Not 0.
Yeah.
Okay. Just make.
Yep. Good question. Anything else about this? All right. Take a look at it real quick, I guess. But basically, this is kind of what we said right between. So, go ahead, Jared.
Oh, so I was gonna ask, if we have the zeros, like if we find the zeros, can we just know that if it's, if the original thing was x to the 4th, then you know it's gonna be that sort of shape where they're both up. So then you go decrease, increase, decrease, increase,
Well, so will every polynomial that is a fourth degree polynomial?
wouldn't it?
I don't think so.
No?
What's the-
If it's a negative in front of.
Well, no, if it's a negative, then it go down.
Right, so-
But if we see it's positive,
Okay, yeah, so that's,
if the leading coefficient is positive, that's.
yeah, that's good. So, yeah, since this is a 4th degree, basically we have two options because it's an even power.
Yeah, so they're gonna go.
It either goes to infinity on the left end and the right end, or it goes to negative infinity on both ends. So because of that, you know, it's kind of bookended by, or like, on the far left side, am I increasing or decreasing? Right, and on the far right, you're going to increase, which is exactly what we came up with, right? So our intervals are 0 points were -3, 0, and +7, and yeah, I think that hopefully that shows that, yeah, we did everything right. And basically what we're using here is the first derivative test. You know, we've got information about literally every real number, even though we only looked at a few. So if f prime changes from positive to negative at c, as x increases, so as you go from left to right, then what's f doing? What does f have at that point, x equals c? If f prime is changing from positive to negative, what kind of point am I describing?
Local max.
That's a local max. And if we go the other way, what do you have? Local minimum. What if it does not change sign? What if it goes from positive to 0 to positive, or negative to 0 to negative? Did I tell you what that thing was called? Or did I just say that it was neither a maximum nor a minimum?
So it was neither.
Okay. So that is true, which is like really the important thing, but
Yeah, you did say so.
yeah, so like, so a saddle point, that's not really important to know that it's called a saddle point, but it is important to know that it's more important for me and for you to know that it's neither of these things. So again, I'll warn you yet again that just because you have the derivative equal to 0 does not mean you're looking at a local extreme. It can be one of these weird things where it just stops increasing before it goes back to increasing again. All right. So same function, different question, right? I want to find all the local extrema of this function. But we already know a lot about what those things are, right? How many local extrema did this function have?
4.
I believe it had 4 intervals of increase and decrease, right?
Yeah, it only has 3.
Right, but so it only has 3 boundary points. So basically what we had is, I'll go ahead and recreate this since it's valuable to know. Where were our 0 points?
3, 0, 7.
Okay. So yes, we had 3 places where the derivative was equal to 0. But those 3 places divided up the real numbers into how many chunks? 4. And what did we say? Decrease? Decrease, increase, decrease, increase. So let's make two columns here. Local minima are going to happen at, how many local minima do I have? 2.
Yeah.
So I'm going to have 2 of them. Do I know their x values?
3 and 7,
Why -3?
because it's decreasing until that point.
Yeah, it decreases to a point and increases thereafter, so that's a local min. And similarly, 7 has that same behavior. Local maxima, those are going to happen where?
At 0.
At 0 only, right? Okay. And just to basically, what are we doing here? If I'm asking for where the local extrema are, I don't want to know only x values. I want to know both coordinates of where they are. So let's get our local maxima first. That'll be the easier one to calculate.
You just put 0 for x in the function,
In that function or the derivative?
the derivative. Because the derivative.
I think I talked you out of it. It's that function.
It's not-
So, but the reason I brought it up is because we really got to make sure what, so f and f prime are 2 different functions and they're used for very, very different things. What does f prime tell you? For this f or any other function?
The slope of a point.
Tells you the slope, tells you instantaneous rate of change. It tells you rates of change, right?
It doesn't take.
What does this thing tell you? That right there, I don't think directly tells you increase or decrease, the function f.
Oh.
Tell me what y is.
Tells you what y is, right? It tells you where. So basically one tells you where and the other, then f prime tells you
How?
how fast.
How fast?
Yeah, tells you, so one tells you location, one tells you rates of change.
Okay, so like in other words, one, like the normal is distance, and then the other one will be its speed.
Right, and that's exactly why those 2 things are related through a derivative, is because one tells you where you are, the other one tells you how fast you're going when you are there. So yes, I want 0 f of 0, which is -5. The other ones we're going to need some technology to get. So yeah, our local minima. What is the y value that goes along with -3, Gary? -464. And what about 7? But
-4,464.
-4664.
4,464.
Sounds good. I'm not going to verify. I trust your abilities to point and judge. But notice, like after we found the intervals of increase and decrease, are we okay with kind of how we flowed to get the extreme points based on that? Didn't really have to do a lot of, didn't have to like retread all the stuff we did before. Any other questions here? All right, so these 2 things here. So I have 2 different graphs. If it's not obvious, I'll say that f of a equals f of a equals g of a and f of b equals g of b. A and b are the same x value. So these graphs, they have some similarities, right? What can we say about f prime comparing you know, function f and function g. Or I guess right now, what can we say about f prime? Not g prime, but f prime.
They will both always be positive.
So we can say f prime of x is positive for all x.
Yeah.
Do we agree with that?
Yeah.
What about g?
Same thing.
No, f and g, like the y values on f are always going to be greater than y values on g.
The y value is on f. So like if I call a point in here,
It's going to be greater on, no, it's going to be less than what it would be on g.
okay. So we can also, I agree with that. I'm gonna go ahead and stick with our talking about derivatives. But I do agree with you that, you know, for any point between a and b, the corresponding g value will always be bigger than the corresponding f value. Okay, I agree with that. Let's stick with f prime. So Jarek has said that f prime is positive for all x inside that interval, right? Is that also true for g?
Yes.
Why?
Because it's still going up, it's just going more, it's going less and less up each time. So the derivative is going to be getting smaller, but it'll still be above zero.
Okay, so it sounds to me like you're saying that on the interval AB, f and g are both increasing for the entire interval AB.
Yes.
Anybody have any pushback on that? I agree with that. So the derivative is positive for the entire interval on both of these functions. What about this new thing? Go, Solomon, go ahead.
So it's increasing on g too, right? The derivative. Is it increasing or staying above zero?
Those are, so that's, I'm glad you brought that up. So Solomon is asking, on g, is the derivative increasing or is it just staying positive? First of all, are those two the same thing?
No.
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 So
It's
let's
still
ask.
positive, but it's decreasing.
So let's answer those both one at a time. We already wrote down g prime is greater than zero for all x. Is that true?
Yeah.
Is g prime increasing?
No.
Okay, so that's a kind of a, but they're different things and it's sometimes difficult to make that difference. So I got this new idea here. We just talked about f prime. Now I want to talk about f double prime. So let's go back to basics here. What does f prime tell you about a function f? Tells you about the instantaneous rate of change, right? So if f prime is positive, what does that mean about f?
It's positive. At that point.
Tells you f is positive?
F is increasing.
It tells you f is increasing. Like, for example, this function, I can move all these points down here. And f would be negative, but f prime, they would still be increasing. So, yeah, positive rate of change doesn't necessarily tell you that the function is positive. So, f prime, if f prime is positive, then f is increasing, right? Now let's apply that by going one layer deeper into these derivatives. What does f double prime tell us about something?
What's the rate of change of the rate of change?
The rate of change of the rate of change, right? So in general, in general, a derivative tells you about the rate of change of whatever function that derivative came from. F double prime, what function is f double prime the derivative of? F prime. So the second derivative is the first derivative of the first derivative. Is there anything we can say about f double prime of x? What can we say?
That it's increasing for f and decreasing for g.
So let's stick with f first. You say f double prime is, you said f double prime is increasing. I don't think I can say that much.
It's positive, then you can say?
It's positive. And that's one thing I really want to harp on because it's a very difficult thing to get your head around. Something being positive is not the same thing as saying that it is increasing. And just to hammer that point home, I'll say this. We've said f prime of x is greater than 0. Now we're saying f double prime of x is greater than 0, right? this right here is equivalent to saying f prime of x is what?
Point C.
Is increasing.
It's increasing.
Yeah. So the first derivative is increasing, which means the second derivative
Right.
is positive.
If the derivative of a function is positive, that means that the underlying function is growing. So if f double prime is positive, that means the thing that f double prime is the rate of change of is increasing, and that thing is f prime. One more way to think about this, so I'll tell you right now, if I haven't made it clear yet, f double prime is positive is true everywhere for the left graph. Because let's go from left to right and draw some tangent lines. What is happening to these tangent lines as I move around and draw them?
Always positive slopes.
They're always positive slopes, but you can say something even stronger. Their slopes are doing what?
Getting steeper.
They're getting steeper. They're getting more positive, right? So the fact that as I move from left to right, those tangents have increasing slopes. That is why f double prime is greater than 0. We got a couple minutes left. Let's talk about G. Can I say anything about G double prime for? Okay. Why is that?
It's decreasing.
What's decreasing?
The rate of change is 0.
G prime.
G prime, thank you. Yeah. So as you move from left to right, G prime is shrinking. So again, I'll draw a small group of tangents here. Starts off pretty steep, getting shallower, getting shallower. So G prime is positive, right? So let's just put it all together. Why is G prime positive?
Because the function is increasing.
Because what function is increasing?
G.
G is increasing. Why is G double prime negative?
Because it's increasing and decreasing.
Don't say it. Too many things to throw pronouns out.
G prime is.
G prime is decreasing, right? And that's kind of illustrated through these tangents. So these rates of change, as I let x increase, these rates of change shrink, they decrease. So that is why G prime is negative. Can I say that G double prime is decreasing? No, that's a little too much for us to say. What kind of thing would we have to have our hands on to say that G double prime? We would need G triple prime, which we're not going to worry about. So is there a verb I can fill this blank in with right here based on that? I think I talked over somebody. Again, is decreasing, right? So because, and so I'll write down decreases. Is it possible for G double prime to be positive and for G prime to be increasing?
In general or not?
In general.
In general.
Is it possible, in general, for all functions, is it possible for simultaneously G double prime to be 0, or so for G double prime to be negative and for G prime to be increasing? That's not possible. So, and the reason I asked that question is because if you say G double prime is negative, you are also saying G prime decreases. Those two things are, those are equivalent. You're saying the same thing in different words. So yeah, now we're getting 2 layers into the derivatives, which can be, it can be tough to keep all those things straight. We'll talk more about it next Friday, I guess. So yeah, just to keep, Monday we're just reviewing. I'll send out a reminder about Tuesday night when I'm going to have a Zoom review thing. Test Wednesday, and then Friday we'll jump back into this. Sure.
So if you have a function that's increasing at a decreasing rate, its second derivative is negative.
And that's, you just described which one of these 2 things.
Second derivative.
Well, which one of these 2 graphs?
Oh,
G, right? Yeah, it is increasing everywhere, but that rate is decreasing. Thanks.